our extravagant outfits because all of our baggages are lost somewhere in Europe. So, yes. Now, I'm personally proud to say that our inverter has reached all the requirements except efficiency, which is 92.5%. So how do we do this? In the last 2 years, we went through the process of research, simulations, design, and testing 3 times, and have reached our final prototype. But our story doesn't start there. Team from our school has been competing at this competition since 2016. During that time, we have built a brand image with which we are recognizable among professors, students, and companies connected to power electronics industry. All of this wouldn't be possible without the greatest help from our mentor, Alexander Milic, and the School of Electrical Engineering is our umbrella institution. Fundraising and public relations is one of the integral parts of Reach Bridges, because with the help of our sponsors, we were able to equip our lab, to produce our prototypes, and to travel here. Also, all of our team members get a chance to meet representatives from power electronics industry and to develop soft skills which they don't get at School of Electrical Engineering. On our social media, we try to present our progress to our partners and the younger students. This way, we are able to reach out to new partners and to popularize power electronics. Every one of our successes is shown on national television and other media channels. We are regular exhibitors at science and engineering fairs in Serbia, and in public we are perceived as top young innovators, awarded with many awards. Now, my colleague Luka will present you our hardware design.
So, based on competition requirements and initial research we conducted regarding system design of the inverter, we decided to go with the 2-stage topology. The first stage being resonant converter, and the second stage being conventional grid-connected inverter with output filter. After simulating LFC, CLL, and LCC topologies, we concluded that the most suitable topology for our purposes is LLC resonant tank. It provides possibilities for both zero voltage and zero current switching, while having a flat voltage gain curve at wide frequency range. When considering inverter topologies, we looked up several inverter types, among which are T-type, MPC, and 2-level inverter. And again, based on the simulation results and research we conducted, but also price that is dictated by the number of components and complexity of the control algorithm, we conclude that the 2-level inverter is the most suitable topology. Our final topology consists of the input filter, H-bridge, a resonant tank, rectifier, and the DC link that comprise the first stage, and the inverter with LCL output filter that comprise the second stage. The first stage provides galvanic isolation and voltage boost needed, while being very highly efficient and having very low volume. The second stage, i.e. inverter, provides possibilities for both single-phase and three-phase operation, while LCL filters output current with very low THD. The first step in hardware design was H-bridge transistor selection. And based on simulations conducted, we derived criteria for this kind of selection. Our analytic calculations show that best MOSFETs dissipate around 6 watts of power when operating at resonance in H-bridge configuration, and around 9 watts of power when we go just slightly higher up in switching frequency. One of the key points of the design of the first stage was LSC resonant tank design. We strive to achieve as high monetization as possible when designing the transformer, so that voltage gain curve is flat at as wide frequency range as possible. According to this curve, we aimed for the Q factor to be around 0.4, and also decided to set the switching frequency of the H-bridge to match resonant frequency of the LSC tank, so that we achieve both zero voltage and zero current switching. We designed the transformer ourselves by considering 3 ferrite core materials based on their high frequency application and market availability. Based on dependence of the dimensional parameter on operating frequency, we concluded that the smallest needed E-core should operate at around 200 kilohertz. We used Litz wires to decrease copper losses in the transformer, and our calculations show that overall power losses in the transformer are around 3 watts. We also examined magnetic conditions of the transformer, and the PEM analysis showed that the highest inductance of the core is in the inner corners and is around 0.2 Tesla, while the saturation of the core, saturation inductance of the core is 0.4 Tesla, and that shows that core doesn't get saturated at all. After the first iteration of our prototype, we redesigned the LSU resonant tank by making two modifications. The first was placing the resonant capacitor on the secondary side of the transformer. That way we reduced the current that flows through that capacitor by around 10 times. We also decided to use leakage inductance of the transformer as a resonant inductor, by which we increased power density of the whole prototype by around 5 times. The calculated resonant frequency of the LSC tank is 145 kilohertz, but the measured resonant frequency is around 158 kilohertz, which we chose to be the switching frequency of the 8 bridge, so that we achieve both zero voltage and zero current switch. The first iteration of DC link was realized using two large film capacitors, which were in the second iteration optimized both in volume and price. And by placing them in 2x2 configuration, we managed to make middle points of the DC link accessible. And we also introduced voltage balancing resistors, so that voltage is balanced equally across capacitors that are connected in series as they age. This is the DC link. When selecting transistors for the inverter, we focused on finding MOSFETs that had as low parasitic capacitances as possible, as dominant losses in this kind of operation with high voltages and low currents are commutation losses. When designing output filter, our calculations show that needed L filter should be around 2 times larger than needed LCL filter for the same amount of ripple. That's why we chose to go with LCL filter. We set its resonant frequency in between grid frequency and the switching frequency of the inverter, and chose capacitor with regards to the reactive power it chose from the grid. We also designed our own filter chokes for LCL filter. We were in that process of the design constrained by dimensional parameters, overall losses in the chokes, as well as saturation of the cores. LCL filter is realized using two different cores, which showed to be the best option we had at the moment of the design. We also conducted separate tests to show that cores don't get saturated even at the maximum currents that flow through them. When designing auxiliary power supply, we tried to achieve minimum number of voltage levels while maintaining galvanic isolation. We realized all these circuits by using cheap buck converters, among which two are isolated. Now I will briefly talk about our printed circuit board design. We had in total 3 iterations of the prototype, and in the first redesign we managed to reduce the size of the PCB dramatically by optimization of LSC resonant tank and also by DC link optimization and overall PCB layout optimization. The third iteration of the prototype is just slightly bigger than the last one because we introduced totally new LCL output filter. Our final prototype is realized using 6 copper layers. Its power density is around 0.2 watts. We introduced the stitching wires to prevent electromagnetic interference and also divided power stage from all other circuits for the same reason. We also introduced thermal wires so that thermal management is improved. The total cost of the prototype is around $270, but it can be further decreased by optimization of all magnetic cores on the board and also by using cheaper wires for the transformer and cheaper DSP. Now, Oz will present you our software design.
Hello everyone, my name is Laszlo. These are my colleagues from the software team, and I will take you to the tour of the software design. First step in designing the software is to select a proper microcontroller. I will point out some things that are nice to have when selecting microcontrollers, like floating point units for fast execution time, enough PWM and ADC channels, and direct memory access for measuring the signal when the execution of the algorithm takes place. You can see here the selected microcontroller and all its characteristics. For the controller algorithm design, we divided our controller into the 2 stages. First stage, which ensures that the voltage at the DC link is kept at a constant rate, and the inverter current regulation, which ensures that the power delivered to the grid is proper. The first stage regulation is done by utilizing the principle known as phase shifting. We shift the one leg of the H bridge in accordance with the other, and in that way we reduce the voltage of the DC link. We lose the zero current switching, but remain at the zero voltage switching. The simple PI controller is used to close the control loop. Now for the hardest part is the inverter regulation, current regulation. Because we want to control our inverter in the DQ reference frame, we first need to transform our system for stationary ABC frame to synchronous rotating DQ frame via the clock power transformation. Given model in the DQ frame is 6-order multivariable model, which further complicates the design of the control algorithm. Another important aspect when designing the current regulation is choosing which current to regulate. We constrain our choices to only single current feedbacks and primarily inverter current feedback and grid current feedback. Dependent on the delay present in the system and the position of the resonant frequency of LCL, one or another can be stable or unstable. And in our case, we choose inverter current feedbacks because it suits our parameters. Because delay is plays such an important part in the designing of the control algorithm, it needs to be further assessed. In our case, we have the three main sources of the delay due to our digital implementation. First is the zero-order hold, which is the inherent property of all digital system. Interrupt routine, which is the delay caused by the shadow register of the PWM module, and the delay present due to the oversampling of the current measurements. You can see the total numbers of delay for our system in the table here. But there is a way to reduce total delay present in the system by utilizing the principle known in literature as advanced scheduling. By finishing the oversampling just before your execution takes place on the shadow register, you can almost completely negate the interrupt routine delay and get a cumulative delay of 86 microseconds for our case, which will further be beneficial for the design of the control algorithm. Now finally, the design of the control regulation. Trust me, I believe this part will be shorter than I started 2 years ago. But first, you need to, because model is multivariable and high order, and you want to decouple your system, the easiest way to do that is to invert the dynamics of the system. But because of the high order and the zeros in the right half plane, you need first to reduce the model of your controller from 6 to 2, otherwise the resulting controller will be uncausal and unstable. So in the image above, you can see the difference between original model, which is blue, and the red, which is the reduced model which we use to project our controller. We use the vector margin to assess the stability and performance of the system, and you can see an image below the dependence of the delay present in the system on the vector margin. We achieve the bandwidth of the current regulation of over 400 Hz. For the grid synchronization, we use the phase lock loop techniques. In the table here, you can see the evaluation of different phase lock loop techniques that we tested on our local distorted grid. Local distorted grid is shown in the image above, and the image below you can see the output of the different VLL algorithms. And we concluded that DSO Jai has the best performance, so we implemented him on our control algorithm. For the single phase operation, we use the SOGI to generate the quadrature signature of the currents and voltages, and use the same PLL and the current controller for the control of the active and reactive power. The results of single phase are a little bit worse than the three phase, but that was expected. Now Luca will continue with the experimental results.
Our experimental setup consists of the inverter itself, the programmator we use to download the code into the microcontroller, and also step-down grid-connected transformer we use to decrease the grid voltage, and power supply and the measurement equipment we use for the tests. After we did the hardware verification, we showed that our inverter operates in stable manner in steady state. We extracted phase currents and one-phase voltage, and also D and Q current components for the microcontroller, and showed them in this slide. We did the same for 1 kVAR and minus 1 kVAR of power. When current step reference change is applied to the inverter, the response is satisfactorily fast, and the Q component of the current shows that current controller is well decoupled. Active power delivery and reactive power compensation were requirements of the competition, but we didn't have the opportunity to test them on grid simulators, so that's why we presented the results from the hardware-in-the-loop simulations. On the left side, in the following slides, you can see phase voltages and phase currents, while on the right-hand side in the top is power factor, and in the bottom are active and reactive power. When the frequency rises from nominal to 62 Hz, active power drops from 500 watts to 0 watts. And when frequency drops from nominal to 57 Hz, active power rises from 500 watts to 1 kilowatt as required per competition. As far as reactive power compensation goes, when voltage rises from nominal to 250 volts, reactive power drops to minus 1 kVAR, and when grid voltage drops to 165 volts from nominal, reactive power rises up to 1 kVAR as required. We conducted current THD measurements and input power factor measurements, and they showed that THD of the output current is 1.7%. We also presented first 7 harmonics of the output current, and the input power factor is significantly larger than 0.99. We conducted thermal imaging that showed that parts of the inverter that heat up the most are inverter transistors and the transformer. After operating for 20 minutes at 1 kilowatt, transformer heats up to around 90 degrees Celsius and the inverter transistors to around 95 degrees Celsius. The last step in the testing procedure was efficiency measurement that showed that efficiency of the inverter is the same at 500 watts and 1 kilowatt and is around 92%, 92.5%. I would like to finish this presentation by briefly reviewing the results we achieved. The efficiency of the inverter is 92.5%. THD of the output current is 1.7%. We implemented both reactive power compensation and active power delivery. Input power factor is satisfactorily high, i.e. larger than 0.99. And we also implemented all required protection, i.e. over current protection, over voltage protection, and short current protection. I would like to thank organizers of the competition for providing us with this possibility, and also the university for providing the space for the competition. Thank you all. We are glad to hear and answer your questions.
From what I see, great work and good presentation. So you mentioned about, I would just have maybe 2 questions. First one is your LLC converter operated under like a frequency modulation or like a PWM?
No, it's phase shifted.
Yeah, but you plotted gain curve against frequency in your design procedure. So why do you do that if you are not controlling frequency?
So when projecting the LLC topology, we made this curve a flat. So in the case we miss the resonant frequency by a bit, we don't shift our gain.
All right. So you wanted to operate exactly as
yes, we made a zero current.
But you kind of you cycle control efficient.
Yes.
Okay, perfect. So you mentioned your efficiency doesn't meet the requirement. Where do you think could be improved in order to hit that target?
We tried to use. We believe that GaN transistors would improve the efficiency because it has lower switching losses, faster switching. We tried to implement the GaN transistor, but we didn't have enough time, and there was a lot of delay from scheduling, and so on, and we didn't have time to test the proper GaN, and we didn't finish the GaN prototype because we can bring it to the test.
I know, it's already pretty good. Because I saw you have a very extensive loss breakdown when you design the entire inverter. So when you add up all those power losses together, does it match with your efficiency measurement? So the whole point for loss breakdown is trying to figure out which one is dominant factor, right? So you can optimize that portion. So does it provide any insight for you to optimize it?
Well, I believe that the major losses comes from switching losses in the inverter.
I see. Okay. All right. Thanks for that.
Why is the testing active power difficult? You know, I thought active power.
It's not difficult. It's not difficult when you test it on the resistance, but this is meant when you change the frequency. We can change the voltage by using the auto transformer, but we cannot change the frequency of our grid because we don't have a grid simulator.
Okay. Now, how confident your PRL will work without none?
We tested it on the three-phase power supplies and
Yes.
it works fine.
Okay.
So, can you go to like slide 25 or somewhere around there? I think it's like the end of your hardware. It talks about what you want, like areas of optimization.
That's the slide.
Okay, yeah. So can you give me specifics for what? Okay, so PCB layout optimization. Like what specifically
Yeah,
did you optimize?
we primarily made it smaller.
Okay.
We optimized the size of the traces and polygons and made just smaller PCB.
Yeah, the first version was the safe version to check if everything will function properly. So the second version is more compact in basically.
Hey, resonant LC. Kondensator na sekundar. The previous slide. Again, with capacitor on the secondary side, you said it. Just repeat.
We also by doing the redesign of LCL field.
Yeah,
LC
also
filter,
resonant
yeah.
optimization. Yeah, those were hardware optimizations. So
Yeah, and that's
on the first redesign.
that reduced the size of the board. So the second prototype with that modifications, it's a lot smaller than the first one.
Label LC.
You mentioned the gain can improve efficiency. Referring to the low voltage side gain or high voltage side?
Yeah, on high voltage side. Yeah.
Because it's fluctuating.
We tried to reduce contagion.
What about low voltage side? What's the nice thing?
MOSFET.
Silicon.
Yeah.
Both. For both the inverter and LC.
So I guess you probably want to swap those inverter MOSFETs out with GaN to receive it. Okay. Do you know if this is a switch loss or conduction loss dominating that part?
For the first or the second stage.
I mean, the inverter, because that's the one we want to optimize, right?
Yeah, inverter, I believe that the switching losses are dominant. Because currents are low.
I see. So how about you just reduce your switching frequency because you already meet your PhD and all those demands?
Yeah, but reducing switching frequency comes at the cost of the regulation, of current regulation, because when you reduce your switching frequency, you increase the delay present in your system, and you can achieve lower bandwidth. And when you connect to the grid with a lot of harmonic distortion, like our local grid, you need that high bandwidth in order to then these harmonics and have this sinusoidal current.
Yeah, because I saw all of the other specifications have been mapped. So if you have sufficient margin there, you probably can sacrifice a little bit those parameters and shift your frequency, power loss a little bit lower from inverter side. So without designing a new whole board. I don't know how that works, but.
Any questions from audience? Okay. Other questions? Please.
You probably said it already, but what was the on resistance of like the low voltage on the low voltage MOSFETs?
Sorry, I don't understand you, could you repeat the
Like
question?
like the on resistance of the low voltage switches, like the RDS on.
Yeah, it's really low, about 0.02 milliohms. It's the lowest we can find
Yeah.
on the market right now. For the market, yeah.
Yeah, I mean that's very low. What is the which company? Infineon?
Yeah.
Yeah, it's included.
What's the voltage rate?
80 volts.
80.
Yeah.
2 milliohm, right?
Yeah.
Yeah, 2 minutes.
About 2 million.
Other questions? Presented very well. When I look at your slide this morning, I said, "This is nice. We should finish it." Okay, no other questions. Let's give them another round. I will look forward to your test because you will be the first this afternoon.
Yes.
All right, I guess right now it's 11:10, nearly 11.
Give me smile, give me smile.
And we have that.
Какое паузирование, нас